Okay, everyone, welcome back. So today, I think I should title today, Can You Draw? We're doing bearings problems, further applications of right triangle trigonometry. We're going to look at speaking of bearings, method 1. So there's two ways to speak of bearings, two methods for expressing bearing. I'll zoom in on this just so you can see it a little better here. You zoom in. Okay, so for starters, when a single angle is given, such as 164 degrees, it is understood that the bearing is measured in a clockwise direction from the north. See? 164 degrees clockwise from the north. So what I always tell people to do is, in this kind of situation, is just, start off with your north-south line and, rotate 164 degrees from the north. Okay, so here's 32 degrees. Notice it's all from the north. All right, so let's just jump right into a bearing problem. Here comes the first one. I'm going to read it, and then I'm going to help you set up the drawing, and I'll probably pause, tell you to hit pause, and you see if you got the same drawing as I did. Okay, method 1. Radar stations A and B are on an east-west line, 3.7 kilometers apart. So you're going to go ahead and start A and B on an east-west line. Now, if you're a little rusty, north, south, east, west. Okay? Station A detects a plane at C, okay, on a bearing of 61 degrees. Now notice, if it helps you, just kind of draw in right there. As soon as they speak of that 61 degrees, that's from the north. So I got to rotate about 61 degrees from the north. That wasn't a pretty little triangle there, was it? So let me make that dot a little bigger there. All right? So there. Station B simultaneously detects the same plane. If you'd like, you can hit pause now and see if you can get the same sketch as me, but Station B simultaneously detects the same plane on a bearing of 331 degrees. Now what I like to do, like I said, I'll put this in I like to have that dashed line, right, that north-south line. And when they start talking about bearing of 331 degrees, okay, if I rotate from here all the way to here, I've done 180, and then all the way to here I've done 270, and then I've got to go a little bit more to get to 331. But the question is how much more, because you're probably going to need to know that, right? So whatever 270, whatever 331 minus 270 is, which is 61 degrees, so you can even fill that in, 61 degrees, okay? Now, you can fill in other pieces of the drawing as well, like if you know from here to here was 61 degrees, then how much is it from here to here? So you start filling in your drawing, basically. So 90 minus 61 is 29. So now know this is 29 degrees, and this is 61 degrees. Aha, so 61 plus 29 is 90. So now you know that this was actually making a right triangle. This last one is 90. Now there's other things you know. You know the piece across from the 90-degree triangle is the hypotenuse. All right. And now in the end, it says we want to find the distance from A to C. Okay? So here's C. We want to find this distance right here. So note to self, we're trying to find a leg of that right triangle. Now, you know from the gate that the radar stations A and B were 3.7 kilometers apart because it says it in the paragraph. Okay? So you know from here all the way to here is 3.7 kilometers apart. Now you can just bust out good old Pythagorean theorem. So a squared plus b squared equals c squared. You know the hypotenuse is 3.7. Okay? The one leg you're trying to find. And in fact, just so my lettering matches, actually, I scratched that. Notice I had just scratched all the Pythagorean theorem part I scratched because I just realized that we don't know both the legs, we only know the hypotenuse, right? So I'm going to go back to that initial. I cleaned up the sketch a little bit too. So from here to here was 61, from here to here was 29. We sketch in that north-south line again. From here all the way to here was that 331, but inside of there was 61. So we had figured on that being a right triangle. And like I said, usually when it's a right triangle, you know, to get the legs, I try to use Pythagorean theorem, but I realized that we don't have both of the legs. So we're going to resort to good old SOHCAHTOA. So think about that a little bit. If you're standing here at, say, the 61-degree angle, and you want to know the piece across from it, because remember, we want to know the distance from A to C. We want to know from here to here. Well, that's opposite over, well, let's see, we know the hypotenuse. Opposite over hypotenuse. All right, so we can use sine. So sine of 61 degrees is equal to opposite over hypotenuse, but we know that the hypotenuse is 3.7. So we can call the hypotenuse x if you like. Go ahead and cross multiply. So just type sine of 61 degrees. Make sure you're in degrees. When you type that out, times 3.7, I'll hit pause. Okay, so hopefully you got about 3.2 kilometers. Remember that, so I'm going to put here approximately 3.2 kilometers for your final answer there. Remember that your answer has, I should say km for kilometers. Your answer only has 2 significant figures because it can't be more accurate than the least accurate in your paragraph, in your measurement, so 2 sig figs. All right, so 2 sig figs on that. Hope that helps. I think it's good for you to see me do it in real time so you can see me thinking through. Okay, now let's scoot that one on down and let's look at a second method for expressing bearing. So the second method for expressing bearing starts with a north-south line and uses an acute angle to show the direction, either east or west, from this line. So let me scoot this down here. So you can see over here, I drew, again, north, south, east, west. But notice when you say north 42 east, you have your north-south line, and then you're moving 42 in the east direction. And notice this next one is south 31 east, so you're starting, you know, you've got your north-south line, and you're going 31 in the east direction. Okay? And again, here we have our north-south line, and it says south 40 west, so I'm going to go, I just like to think the direction, I'm going to go west 40 degrees. And when you say north 52 west, okay, 52 west from your north line. All right. Well, the best way, like I said, the best way to deal with these problems is to jump in. See what you can do. See what you can sketch. So this one I kind of cheated because I have a little mini sketch there, but I want you to, you know, probably see me do it in real time. So a ship leaves port and sails on a bearing of north 47 east. So with these problems, what I always do is I have my north-south line, and I think about what that means. Okay, 47 east, that's that direction. 47 degrees. For 3.5 hours. Now the fact that it's traveling for 3.5 hours, don't worry about that. And it says it leaves port, by the way, so I'm just going to write the word port here. Okay? We won't worry about the time until later. But it turns, here's the trick with these, it turns and sails on a bearing of south 43 east. So when you see the word turns, draw another north-south line in there. So north-south line, north-south line. Draw another north-south line in there. So it turns and sails on a bearing of south 43 east. So that means I'm going to go about 43 in that direction. Okay. Okay, and what I always do is when I know 43 in that direction, south 43 east, and then I draw in, you know, my terminal side, okay? And I'm going to do that for 4 hours, okay? And then the ship's rate of speed is 22 knots, so find the distance that the ship is from the port in, you know, in the end. So we can call this point B, we can call this point C, and then we want to know in the end, you know, how far is it from point A to point B. And like I said, I'll zoom in. You can see that the drawing I'm ending up with is very similar to the little mini one that I have there on the left, okay? Now let's take a little look here. There's another thing that we ought to know. When you draw in those north-south lines, you're really dealing with parallel lines, right? So you know that alternate interior, think about this. I'm going to draw this in black. Okay, here's a north-south line. I'll highlight it in black. Here's a north-south line. This will help you see it. If from here to here is 47 degrees, then guess what? From here to here is also 47 degrees. How come? Note to self, alternate interior. When we talked about alternate interior angles, two parallel lines cut by a transversal. In essence, this AC here is a transversal. So those alternate interior angles are equal. All right, so if you know from here to here is 47, and you know from here to here is 43, well then 47 and 43 make 90. So that happens to be a 90-degree triangle, hence I'm going to zoom in. See? From here to here is 47, from here to here is 43, okay? Now we just use what we know about distance equals rate times time to figure on the rest. So let me zoom back out here. Okay, these problems take time and they're very intricate. So you know distance equals rate times time from algebra. So the rate is a 22 nautical miles per hour. So I'm going to write 22 nautical miles per hour. But, you know, on your first path you were traveling for 3.5 hours. So whatever 3.5 times 22 is, aha, that's 77. So if I zoom in on this picture now, you can see I went 77 nautical miles. From here to here was 77 nautical miles. How much is it from here to here? And notice we are dealing with a right triangle, so it's like if we know this leg and we know this leg, it'll be easy for us to find the hypotenuse. So again, back to distance equals rate times time. You're traveling at 22 knots, and for the second stretch of the trip, from here to here, you've taken 4 hours to go the second stretch. So 4 times 22 knots, 88, right? So I zoom in on this picture just so you can see. Okay, so now we know it was 88 nautical miles to get from here to here. And again, just using that good old distance equals rate times time, that you were going 22 nautical miles per hour for 4 hours, that's 88 nautical miles. And now, right at the end, we're trying to get from here to here, and we know that's the hypotenuse. The trick is that that's the hypotenuse, because it ended up being a 90-degree angle, and the piece across from the 90-degree angle is the hypotenuse. So now it is just leg squared plus leg squared equals hypotenuse squared. I know I tried to use that in the problem before this, and it didn't turn out we had enough information to use that, but so let's go for it. So we know that 77 squared plus 88 squared equals the hypotenuse squared. I'll hit pause as you crunch that out. Now this is very interesting actually. You probably end up, after you take the square root of 77 squared plus 88 squared, you probably end up at 116.9, let's say. But now's a good time to talk about sig figs. So the hypotenuse is, 116.9 miles, nautical miles. I'm just going to write NM for nautical miles. But my answer key has approximately 120 nautical miles. And you say, well, exactly right here, it has 120 nautical miles. How come? Because of the sig figs. So believe it or not, I know this is where it gets intense. The sig figs, there's 3 of them, because, I'm sorry, 2 of them. Believe it or not, the number 120 only has 2 sig figs. That 0 at the end is not considered a significant digit. And notice the numbers in your measurement here have 2 significant digits. So, some teachers are really fussy with sig figs. I'll just let it be known that, 116.9 is right. It's just that the sig figs on that aren't right. Okay? I'll hit pause as we scoot the notes down. Okay, and one last example for us today, a twist on the classic angle of elevation problems that we did last class, actually. I'll read it to you first. Francisco needs to know the height of a tree, and from a given point on the ground, he finds the angle of elevation to the top of the tree. Now remember, angle of elevation is always from the horizontal. So he finds the angle of elevation to be 36.7 degrees. So I'm just going to write that in there. Okay? And that is to the top of the tree. Love my tree there. He then moves back 50 feet. So I'm just going to write, okay, now he moves back another 50 feet. And from the second point, from this point here, the angle of elevation to the top of the tree, there's the top of the tree, is a 22.2. It makes sense that it's smaller visually. Find the height of the tree to the nearest foot. So originally, from here to here, remember, we didn't know what that was. That was x. From here to here was x. Okay, so you can use what you know about similar triangles. I'll hit pause if you want to give this a shot yourself. Okay, so let's label, and I have the answer written here, but just ignore that. So remember, you're interested in the height of the tree, so I'm just going to write down a few things that we know, and consider that there's similar triangles here in a moment. So let's say we're here at this lovely angle here, the 36.7. So we know tangent of 36.7 is equal to opposite over adjacent, so opposite over adjacent. So the height of the tree over the adjacent piece, which is x. So you just kind of write down everything that you know. Okay, check, we know that. But now put yourself at that 22.2 degree angle. All right, well, we know that tangent of 22.2 degrees is equal to the height of the tree, I'm just going to call that h for the height of the tree, over the distance from here all the way to here. Okay? And in fact, I'll highlight that in black, the height of the tree and the distance all the way from here to here. Well, that would be 50 plus x. Okay? So we know a little bit at that moment. Then we also know that we have similar triangles going on here, and let's see if I can pick something different from the color palette here. Green, yes. Okay, similar triangle says this. Little leg, see I'm highlighting in green, little leg is to height of the tree, as big whole leg is to height of the tree, right? So I'm going to scoot this on down. What that basically means is that both of these expressions here, we could isolate h. So if I cross multiply here, I know that h is tangent of 36.7 times x. But I know in this expression, tangent tangent of 22.2 times 50 plus x, I know that that will also, give me an expression for h. So the thing is, if they're both h, then we can set them equal to each other and solve for x. Now, that can become a little tedious with all the decimal crunching. So what I'm going to do is just kind of lay out the basics so the podcast isn't too long. So you'd be laying out tangent x, so this expression basically x tangent of 36.7 is equal to tangent of 22.2 times 50 plus x. Now remember that tangent of 22.2 is just a decimal. So you can send that through, note to self, distribute. So you can send that through and basically say tangent of 22.2 times 50 plus tangent of 22.2x is equal here, on this side, tangent of 36.7x. And what you can do is you can collect all the terms that have an x on one side. So I'll scoot this on down so you can see that. So what it would end up being then, so if I take every term that has an x in it and get it to one side of the equal sign, then I'd end up with tangent of 36.7x minus tangent of 22.2x equals basically 50 times tan of 22, I should say tan of 22.2, tan of 22.2. Okay, now because your computer often wants an exact answer for the homework, you're supposed to not start typing in these decimals until the very end. So you're going to factor out x as the GCF, so you'd have tan of 36.7 minus tan of 22.2 equals, 50 tan 22.2. So in the end, you can probably see already that x ends up being 50 tan 22.2 degrees divided by this lovely expression, tan of 36.7 degrees minus tan of 22.2 degrees. And it's going to be so important for us to keep writing degrees because in our near future that's going to change. Now then right at the end, basically you would type all of this out. So you would type all that out in the calculator, and eventually you would arrive. Actually, hold the typing. Like I said, hold the typing until the end. Don't type that out yet. Remember, note to self, that you just did all that sweat equity and arrived at x. I'm actually going to scoot back to the original problem. So the original problem, though, is you want the height of the tree. You don't want x. So I'll put this in. The thing is, to get the height of the tree, you're just going to have to take tan of 36.7 times x. So you just have to make sure you're solving for the right thing. You want the height of the tree, not the x. So let me scoot that back down. So height of the tree, you just take tan of 36.7 times x. So after all that sweat equity, and you arrive at your x, but know that to get height, note to self, I'll have to take this lovely expression and multiply it by tan of 36.7. So tan of 36.7 degrees times x, where x is all of that. Eventually, you type all that out and you're going to get approximately 45. So height ends up being approximately 45 feet. So that one is pretty intense with the number crunching, and I usually put that as extra credit. Okay, good luck out there.